Hey, welcome everybody. Kirill, it's great to have you here with us, and welcome everybody here tuning in for our webinar. Today we've got an exciting session to talk through, of course, reverse engineering. So we're going to be talking about, some of the getting into the nitty-gritty, a little more detail today with laser scanning than in some other applications. This is where you say rubber really meets the road, laser scanning, when it comes to understanding the real context of things, structural integrity and soundness of elements and buildings. And how do we measure that in some ways? Or Kirill, how do you measure that? How does chief engineering measure that? How is it that you really know the integrity of some of these items, down on the lowest detail, but then how you apply this technology on a large scale as well in areas. So talking about, space management and asset, maximization, making sure that your clients are using their existing structure and their existing spaces to the absolute best. So we will get started here in just a minute. We're going to give another 1 minute or something for everybody to jump in. But I think, I guess as we're getting started, Kirill, if you'd like, why don't we just begin with some introductions as everybody's jumping in. So I'll introduce myself. My name's James Mosman. I'm here with Reality Capture Network. I've got experience in scan to BIM space. So this is a topic that hits on my interest a little bit more. This is where I've worked, but not quite in the same detail, not to the degree that you have. So Kirill, if you'd like to introduce yourself, please take it away.
Absolutely. And firstly, thank you, James, for having me here. I know we had a lot of conversations in the past, but not in this format, perhaps. So I'm quite excited to do this actually with you.
Yeah.
And I like that you mentioned some of your experiences. I mean, you introduced me to some of those technologies. I think it's fair to say that as well. But my name is Kirill. I'm a licensed professional engineer. I specialize in thermal and fluid systems, but due to the nature of my experiences, I've been exposed to way more than that. And I mean, as you can see, today's topic is mainly structural, which probably the first couple of years of my professional life I've been heavily invested in, and I had a great mentor who is unfortunately no longer with us, and I'm quite thankful to him for all the experiences that he passed along to me. But let's see, at Chief, I'm a project engineer, but I'm also a scanning manager, so I oversee majority of the scanning operations. At Chief, I'm responsible for development procedures, also for evaluating a need for a new equipment, which is again something we worked together on before. And I mean, some of my passions are going to be when it comes to engineering. I'm quite involved on computational fluid dynamics simulations, a variety of different simulations, FEA, which we will briefly touch today as well, because it's a great tool, great mathematical concept when it comes to structural analysis. So some of the softwares utilize those concepts. That's going to be reviewed today as well. So that's
Awesome.
that's kind of what I do. I mean, I've done, I would say, quite a bit of scanning. I've been on site a lot, dozens and dozens of projects, scanning for 12, 15, sometimes 16 hours. Throughout my career at Chief, I pretty much I wore a lot of hats. Let's put it that way. I started just doing drafting and scanning. On the first day, I was given a Faro scanner, and I was told, go read the manual and figure out how that thing works. And I've been here ever since. And I've done probably just about everything you can do within Chief. And I'm here today to share some of those things.
Yeah, that's perfect. So let's jump into some of that. Let's start talking a little bit more about the projects, that you've worked on, the different technologies, saying that you're wearing many hats, wearing one of your best hats right now, the RCN hat, I see, of course. But wearing, lots of different hats. And on the technology side, ranging from obviously the needs, solving your customers' problems, what technologies do you apply to different problems? How do you blend those together? How is it that you wearing many hats can kind of blend that into one holistic solution? And really, again, we're looking at things from an engineering perspective, but relative to, to the solution that the owner wants, at the end of the day. What is it that you use? How do you use that? Please start jumping into some of these projects that you've described.
Yeah, absolutely. And I can barely see your head, by the way, perhaps because of the lightning, but
Still there, still
still
RCN.
there. Still there. That's good. Okay, so ultimately, Chief Engineering is a consulting company. If I were to explain majority of our projects, it's going to be along the lines of process improvement, process developments. Either it is either we're looking at existing process or we're creating a completely new process with an industrial facility. I would say 95% of our work is within industrial sector. We don't do much commercials. We don't do residential, and we prefer to stay on that side. And we do, I want to say just about anything on the industrial side. We will do mechanical, we will do structural, we will do electrical, process, mass balance, whatever engineering help our customer might need. We'll always try to help with that. And we can help with projects starting from a simple equipment modification or placing a new equipment to placing a new process or modifying a new process with an existing facility, or perhaps placing a new facility with a new process. But one thing that is common throughout all those different projects that we do is actually scanning, because our designs can only be as accurate as the data that we're working with, which is quite crucial. I mean, the geometrical dimensions is arguably the most important aspect when it comes to the design work, because when we need to place dozens of pieces of equipment, when we need to run a lot of pipe, we need to make sure that we have space. We need to make sure that we have, the place. We have not too many interferences, that it's feasible to put certain pieces of equipment where we think it's going to go. And scanning helps us quite a bit with that. Now, we predominantly utilize terrestrial scanning due to the nature of its accuracy. And you will probably hear me saying accuracy quite a few times today, because accuracy for us is extremely important. We do other types of scanning. We have a mobile platform. We do aerial scanning, and we also do detail scanning. The main objective of today's conversation is going to be terrestrial, because in my experience, it's the most suitable one when it comes to structural assessments. It's accurate enough for us to be able to make a good judgment on beam sizing, pretty much existing steel sizes. And we try to utilize other methods, and they either turn more costly if we talk about more detailed scanning, or not accurate in some cases, which I hope that's, with improvements in mobile scanning, I imagine that technology is rapidly developing right now, even as we speak, and that will change quite soon. At least that's one of my hopes. For some of our projects, we do utilize aerial scanning. We have a couple of drones. We have a LiDAR unit for the drone, but unfortunately, it's not quite accurate for what we needed to do. We tried quite a few times. Unfortunately for us, right now, the photogrammetry is still the better way to go, without spending hundreds of thousands of dollars, obviously. But on some of the projects, we still utilize the aerial, mostly photogrammetry. Terrestrial is going to be the bulk of what we do when it comes to scanning, simply because the accuracy seems to be appropriate for majority of our work. If we're looking at pieces of equipment that we tie in, I need, let's say, good details on some of the flanges. If we're looking at heat exchangers, I need to be able to see good details on things. Again, structure wise, I need to be able to determine sizing on some of the structural members, which we're going to get into more a little bit later. But we try to, every single project, with a few rare exceptions where all we do is, let's say, code compliance calculations, or if we do some other geometrically irrelevant activities, we will do scanning. So I would say 90% of projects that we do require scanning, and most of the time is going to be terrestrial. Now, one of the things that we do is also detailed scanning, and we have a detailed scanner which is capable of about 9-10 thousandths of an inch accuracy, which for the most projects, even when a large amount of details is required, is enough. We have encountered situations when it's not. For example, our common friends, Kirill, worked on a project recently where he had to recreate a pattern on a filter, which on paper our accuracy was very close, but unfortunately the conditions, which in terms of reflectivity were not optimal. So even that solution was not ideal, but we managed to overcome that issue, of course. Now, in some cases, we can check some of the products. So, for example, in this case, we scanned some of the products from a customer, and we're looking at deviations within the final product.
So what type of applications, when your customer has a problem, on a site, obviously the customer, I assume, is not telling you what type of equipment you need to use. He's saying, we have an issue, we want to, run some sort of expansion, we'd like to introduce new equipment. How do you navigate whether to implement this type of technology? What kind of applications do you use the high detail scanning for, in your structural or mechanical features relative to the terrestrial, which is often a good, like you said, you do that on almost everything.
Mm-hmm. So the detailed scanning takes way more effort. Mm-hmm. So it's always depends on how much investments we are willing, or our customer is willing to put for a very, very precise scan of something versus perhaps a slightly less accurate, but a scan that covers, let's say, 90% of what we need. If that's sufficient, then we will try to stay with terrestrial. Hand scanning on site can be troublesome because it does require, in a lot of cases, it does require our customer to, let's say, stop production. Or sometimes it's not the problem, because if, let's say, they need to reverse engineer a piece of equipment or a part that needs to be replaced, and let's say it's a very old piece of equipment, a part is broken and no one has any drawings, and no one is even out there to supply the drawings. So it's either to pretty much stop using the equipment or try to reverse engineer a part, which in that case they could send us a part and we could do a detail scan on that. So it just depends on feasibility. I think feasibility is always a question. I think it always comes up. Ultimately, what are we trying to do, right? I think the main question is, what is our deliverable? Because it's going to be driving the decision behind what kind of solution we're going to utilize, right? Again, our customers typically don't know what different tools can deliver, and it's kind of our job to navigate them, but also to keep in mind feasibility of certain solutions, because we can't simply desire the highest accuracy everywhere throughout all the projects, throughout all the applications. It's simply not going to be feasible, and it's going to hurt the customer. So it's our job to balance between accuracy and feasibility to some extent.
So for your terrestrial use cases, you mentioned a couple examples. If you're putting in a new heat exchanger or something like that, you needed to tie into existing setups pretty well. Do you implement more of the detail scanning on those applications? Is that pretty rare? If you need flanges to match up, you're putting in a new tank and you need, things to tie in perfectly, are you able to solve most of those issues just with your terrestrial scanning?
Yes, most of those issues are solved with terrestrial scanning. Implementation of detailed scanning with equipment that we have, at least, is not as easy, I would say, especially connecting them.
Mm-hmm.
So most of the time it's just either one. We can combine. So for example, if we're talking about a piece of equipment, we can, and it's rather large, we can scan a piece of equipment with terrestrial. But if we have certain parts that are of specific interest and have certain requirements on accuracy, then we might go and do the hand scanning on it too.
Okay. I think that makes a lot of sense. Please keep going.
Mm-hmm. Yeah. So what we found for ourselves is that terrestrial is kind of a happy medium between variations of mobile platforms and photogrammetry and detailed scanning. Typically, it gives us sufficient accuracy and sufficient details on things that we need, including structural, and that is the main concentration of today's conversation. So typically, I would say in a lot of places that we do work, some things were not engineered properly. Let's say it that way. Sometimes things are put in place without proper design in mind. Sometimes certain equipment is placed by a maintenance crew, let's say, and a couple of steel members are added, or even an entire platform or mezzanine is added, but it's never analyzed. And sometimes it works. That's not how it's supposed to be done, obviously, because typically it's done without any regards to code. But regardless, sometimes when we need to add new equipment to some of the structures, we find out that there are no existing drawings. No one really knows what's out there, unless we just go and look at it. There's absolutely nothing. And we encounter situations where existing drawings simply do not exist on a variety of structures more often than I would like. And in those cases, especially when we want to alter those structures or we want to add new heavy pieces of machinery, whatever we're doing, we have to look at what is that existing structure. Can we use it? Because if we can't, then we're talking about completely different budget, right? So assessing existing conditions of structures is extremely important because it allows us to evaluate the existing structure, obviously, and then if we need to make modifications to implement new machinery or simply to support new loads, let's put it that way, we can do that too. But without the assessment, we can't really tell what exactly we need to do to the structure to be able to produce the design that our customer needs. So, as I mentioned, terrestrial is probably for us seems to be the best solution when it comes to accuracy. And today I'm going to use one of the examples that, again, our good friend Kirill had worked on, I think, earlier this year. So shout out to him for doing great work.
One quick point, just for everyone listening, if anyone here has questions throughout, we do have a little chat and question and answer box. So please feel free to ask questions. We'll answer them, or Kirill will answer them as we go through, or we can answer them all here at the end. So if you have questions on workflow, technology, best practices, please feel free to just drop questions here in our little question box.
Thank you for mentioning that, James. So I'm going to be using this project as an example, which is ultimately there is a mezzanine within a facility of one of our customers. And we needed to evaluate the existing mezzanine for addition of new loads, Let's just put it that way. Obviously, there are no drawings. So what are we going to do? We're going to go and scan the existing structure. Now, when scanning structures for the purpose of structural analysis, we have to keep that in mind, because building a redundancy when it comes to, let's say, scan placement, I think it's quite important, because what we really need to look for is multiple angles when it comes to viewing the steel members, right? We don't want to view, let's say, an L shape from one angle, because then we can't even differentiate between an L shape and a tube, right? And even if we can say that it's an L shape, can we really determine what's the thickness of it? Is it going to be a 3/8? Is it going to be a half inch? Is it going to be a quarter? So redundancy in scanning stations is quite important, because it allows us to identify steel members with a less probability of an error. So once the structure is scanned, we obviously process the data, and we use an as-built software. We personally use Edgewise. I see James, you smiling.
Yep, from my alma mater, say Clear Edge 3D.
Yes, of course. I know there are quite a few other solutions available in the markets. We just personally use this one because we got a discount. But
It's a good tool. That's
yeah, yeah. It's definitely, it does what we need it to do. For those who don't know, some of those softwares can semi-automatically extract steel members. They can extract pipe, ductwork, and just use internally built specs to kind of size the steel members, piping, whatever specs they really have built inside them, and they allow us to kind of semi-automatically extract them. Obviously, just like any other piece of software, it requires oversight. It definitely likes to put wrong shapes where they don't belong sometimes. But as long as we keep an eye on it and really inspect every single member, we get pretty good results. And one thing it allows us to do is generate those cross-sectional views that I showed on the top right side of the screen, which we can use to judge the steel member sizing. So again, multiple angles around the steel is quite important, so we can have a better cross-sectional view, and obviously the accuracy, because it will give us a better overall steel sizing. Because some of them, for example, if we're looking at I-beam, which is what we have on the screen, the difference between, let's say, W12 by 14 and W12 by 16 is very small, and it has the same web, it has overall the same dimension, it just has slightly different flange thickness, and we're talking about fractions of an inch. So it's quite hard to determine if we have a lot of noise and if our accuracy is not there. So that's the driving factor besides behind using the terrestrial scanning. I think it provides quite a clean data, as you can probably see on the screenshot. And most of the time we can determine what the steel member needs to be. And if sometimes we can't, then we just go with a more conservative solution.
So do you ever, on these sites, do you ever bring out your detail scanning or bring calipers on site to when you need to get that? I mean, like you said, W12 by 14, W12 by 16, they're really close. For some instances, maybe it matters. A lot of the time, like you said, you play more conservative. But when you're out scanning, if you foresee that being an issue in your on-site scanning, do you measure things with a caliper, make notes to bring back, when you're doing modeling itself? Will you ever hand scan things like this? Or if you run into rust sections, do you ever do detail scanning on rust when you're running analysis? If you run like rust analyses too. But when you get into those detail structures, do you ever lean heavy into the more detail scanning, or do you just take that into consideration on the backside, still leveraging what you captured from the terrestrial scanner, and then just adding the the conservative piece to it when you're back in the office?
So hand scanning is quite not problematic, but it's not convenient. I think some of the hand measurements, like calipers on just measuring thickness, is still something that we do sometimes. You can't completely get away from it, and
Oh yeah,
I don't think we want to get away from it, right?
yeah,
Those tools are out there to make processes more efficient, but we should never disregard things that worked for ages.
yeah.
There's a lot of
I
value
agree.
in it, and yeah, absolutely, we still use that in some cases. Hand scanning, not so much. Rust is a very interesting topic that you brought up. Typically, I mean, if there's a lot of rust occurring within a structure, that's something that a licensed structural engineer will have to be on site for. Not even me, because I'm not a licensed structural engineer, perhaps. Um, and typically, on that end, we can try to evaluate. Okay, a certain portion of the cross section of the beam has been eaten by rust, and we can reduce the structural capacity of the steel members on the software side if needed.
Got
So
it. So more of a site detection, not something that you need to take extra tools, caliper. And I mean, I totally agree. I think the technology is awesome, but minimally, at least to create a base standard, knowing that your terrestrial scanners are registering correctly and your sizing is exactly accurate. I think calipers are a great way especially detail elements to make sure that, you know, that things are correct, that your sizing is correct. But for something like rust or details, maybe if you're designing, you got to tie beams together for new construction or renovative work, uh, maybe that requires some more detail. But most of the time, inconvenience of the detail scanner, not necessary. It just adds cost, adds time, and the terrestrial for all of these reversed application scenarios, terrestrial will get you all the way there most of the time.
yeah, absolutely. I mean, the detail scanning, I don't think we used it on structural ever, I think. And we looked at quite a few different scenarios. We looked at repairing of structural columns because of the forklift operators have been racing through the facility and bumping in everything they can bump into. We've looked at quite a few of those, which between the hand measurements, but we will still do a scan. Actually, on one of the projects like that, what I did was we did a we did a terrestrial scan around, and then we modified a shape um, of the I beam at the place of deformation, recalculated the properties for the column, applied all the loading on the column, and we looked for a local buckling. And we also looked at how much capacity has been reduced on the column, which in that case, while it looked not that great, it actually wasn't that bad. I think there was about 10% capacity reduction. And with the loads that the column saw, there was no possibility for local buckling at all. So I think hand measurements are still important, especially when it comes to details like that. But hand scanning, again, with the tools that we have, I don't think it's viable necessarily. I imagine maybe there are hand scanning tools that are more robust in a way, but we did not really encounter a need for them yet. So I will just leave it at that.
No, I think that's perfect. I mean, the need that you described is a pretty, you know, it's a pretty demanding, application in some ways. A buckle on a structural column, checking if that's still sound, and being able to do that with a terrestrial equipment. And then talking on the field side, this technology is super useful, of course, but it doesn't disregard the work that people do in the field. It makes it, available in the office. It makes it available so that you can do everything, but you're still
Mhm.
taking precautions. You're still making sure to at least double check measurements, using calipers, or, actually hand measuring things to check those, and not opening yourself to possible risk by just, diving totally into the scanning, but you're using that in its best value and safely checking everything on site as well.
Yeah, we try to double check things as much as possible. Sometimes it depends on how much access we have to certain things. For example, if we don't have a lot of access to some of the steel, which might be, let's say, 20 feet in the air or 30 feet in the air over equipment where we can't even bring a lift, I mean, we'll have to go with conservative assumptions.
Mm-hmm.
Regardless of accuracy of your solutions, whatever it may be, a hand measurement tool or a scanner, um,
Mm-hmm.
there going to be a level there's going to be a certain level of assumptions that is being made, which is going to dictate the level of conservatism, I think.
Yeah, yeah. As we did just get one question on that still hits a little on the details here. So this is on detail of hand scanning. Question is, when you say hand scanning, does that include the Faro Orbis with a flash scan?
Um, I have
Are you?
not I have not used that one. Uh, that's the isn't that the new mobile scanner?
Yeah, it's so
Mhm.
if I remember correctly, which I think I do, the Orbis is the after Faro purchased GeoSlam, and their
Okay.
flash scan, the remake of the GeoSlam. So the hand scanner I think that you're talking about is really in a different category
Hmm.
from the Orbis here, where we go in terms of accuracy, low to high, Orbis terrestrial hand scanner. We're talking more of like a Creaform type of scanner on the hand scanner, right? Something for manufacturing, fabricating parts, like you said, sub-millimeter accuracy.
Yeah, exactly. In fact, we have Creaform Handy Scan.
Okay.
That's exactly what we're using. So I think the Pharos slash GeoSlam unit, I mean that's definitely going to fall under the mobile platform. So sorry for confusion if it caused any. But yeah, when I typically talk about hand scanners, honestly, I'm talking about high accuracy devices, and um, I kind of lump all of the mobile scanners together.
Yeah, I think that's perfect. And I think that's a good question too, to draw a little distinction, especially because we're keen on talking high accuracy here, make a distinction that these hand scanners, these are more tedious, the more tedious, not not intended for mass data collection for room or space layout. You're certainly not capturing square footage with your Creaform in this case, scanning an area. The focus focus is the exact opposite, maybe even blended with another hand scanner set applications, but hand scanning so that you can get the most detail in areas where the most detail is needed. And terrestrial might not capture that. You have those slides on I think a Bolt or the Lifesaver, even, being able to create a mesh
Mhm.
on a Lifesaver, and have it detailed enough so you can read it.
Yeah, absolutely. I mean,
Yeah.
Faro does have a hand scanning solution. I believe it's not as accurate as some of the Creaform scanners, but um, I believe it can be a good option. I think it's kind of a middle ground between what I'm talking about and a terrestrial scanner, from what I remember.
I think so. Is it the Ferro arm? Or maybe that's even different. Maybe that's on the more
Uh,
detail, but
Arm is there too, yeah.
yeah. Yeah, so closer to that side.
Hmm.
But I think that's great. I think you answered that one well. So let's keep going here in the well, steel modeling and analysis.
Hmm. Yeah, absolutely. So once the steel is as built, we have two things. We have geometrical representation of our structure, which is quite important, and we also have sizing for all the steel members, which is precisely the information that we need to pass to the structural software. Now, there is going to be some cleaning steps on the way. For example, some of the columns, when as built, none of them going to be perfectly vertical, but for the analysis purposes, it's much more beneficial to make them vertical. I'm not going to go into those steps because I think it's going to be kind of specific to software. Um, I do it on structural software, hence we use RISA 3D for those purposes. Other people might be using something else like Tekla or other structural softwares. There are quite a few of them out there, and they're very similar in its nature. But what we typically do is we take the as-built model from the EdgeVice and put it into Revit, because Revit can communicate directly to RISA, and it has capability of converting our physical members into analytical members, which is what we see here in the middle. So what we do is we extract analytical members from the physical members that we did an as-built in the previous step, and then we export that into RISA, which is a pretty seamless transition. And you can see the actually direct export into RISA here on the right side. And a little bit of background on RISA for people who are not familiar is ultimately it's it's a simplified version of FEM software, I would say, and it's tailored towards structural, where it has a lot of steel members specs already built in there, and all you need to do is pretty much represent your geometry, assign member sizes, and then you can add your loads per whatever you're using. For us, it's going to be ASC 7. It's kind of like our Bible, where we're going to get our load combinations, everything from live loads, dead loads. If we outside, we're going to have winds, we're going to have seismic loads, and we can load the structure. We can take a look at how close are we to failure on pretty much all the members. So once in RISA, I do most of my cleaning work in RISA. You can probably see some of the members are not on the same plane necessarily, which on my ends can be pretty easily adjusted. But we're still working on some of those workflows. And once it's in RISA, we can apply our loads. So we take our new loads and apply the combinations from ASC 7, and we'll look at, okay, what's going on with some of the steel. Are those members going to fail? Is that going to be sufficient? Are we going to be close to failing, or is there's going to be too much deflection? We can really look at what's going to be happening once the new loads are applied to the structure. And from that, we can propose our modifications, right? Because sometimes, and I would say pretty typically, if a structure was designed for a specific load, if we add more, we probably have to modify. So in this case, we added quite a bit of bracing to the structure to be able to accommodate newly added loads, which is fairly typical. As you might have seen, there was not a lot of bracing on this existing structure, which once we add new dead loads up high in the air, the seismic forces will kind of dictate some of the additional steel in the structure. Now, once we make our changes, we can send it back to Revit pretty much. We can produce our drawings and give it to customer. We don't do the construction ourselves, but we can assist with the management aspect if we need to, and we can also do the verification part, which brings me to the last part that I wanted to talk about, and that is being implementation of control. So we have a scanning total station. Thank you, James, again. Um, and one thing that our customers sometimes want is once, let's say, our steel modifications have been implemented, um, they want us build drawings. They want us to go in and verify that first of all everything has been installed, and then has everything been installed correctly. And it's quite a big question. And the first step for it, as for really majority of things here at Chief, is going to be let's go back and scan it, right? But the big key here is we want the new point cloud to be aligned on the same and share the same origin as the old point cloud, so we can actually compare our model with the point cloud. So we try to establish control grids on majority of projects, especially if we know that we're going to be coming back, which allows us to, if we ever need to come back, tie in into the control, and by default we are on the same origin, which helps us a lot because of things like we use Verity, for example, which is another software in the same suite as Edgewise. I'm not sure of alternatives to the software, but what it allows us to do is it allows us to generate reports on some of the steel modifications that we do. And what it does is it finds if steel members have been installed within a certain tolerances, which are controlled by us. It also allows us to identify which elements have not been installed at all, which actually happens more than you would expect. Sometimes people miss bracing, sometimes people even miss I-beams. It happens all the time. But here I have an example of a small reports where majority of things are actually within the tolerance. And I have an example of just one of the pages from the report where we take a look at one of the steel pieces, which in this case is a tube, probably not the most important part, and it's about 0.7 inches off. Not going to be an issue, but with some items, location can be quite crucial, and especially some items when not identified, we need to definitely bring that up. And some of the solutions help us to identify those items. Some of our customers actually like having the report in addition to the as-built drawings because it's quite hard to quantify those items. So on some projects, we also do the verification once the installation is done. So with that being said, I think that pretty much outlines the life cycle of a project, right? From the beginning, we start with scanning, so we gather the data that we need for us to do evaluation of existing steel, do modifications. Then we can go and gather more data, make sure that everything has been placed the way we need it, and that everything that we put in the design is there, right? So overall, that's the workflow that we use, and it seems to bring quite a bit of value to our customers. And we're still working on developing some of the steps within the process, but that's pretty much the outline of it.
Thank you, Kirill. I think that's great. I know we do have some time now for questions. I have a few questions myself that I'll tee off, and some of it even here, just still on the verification side. You talked about using it as a sort of as a construction verification tool to make sure that things were built correctly And then, sometimes things are missed, they're not built, or some things are not built, to spec. Do you use that at all to come back to your one of your earliest examples when you are on existing site spaces and things need to tie in? Do you use it for verifying that things, maybe like anchor bolts, even, or some elements being used for construction are correct for, like tank placement or heat exchanger uh, placement? Do you ever use that as a model for? I guess it's still on the same vein as construction verification, but when you're putting in critical equipment, is that something that you just create an as-built model, or are you out there checking on the field relative to, whatever equipment you're bringing in to say, yep, I know before that tank gets dropped into place, it's going to fit. It's going to fit. We're not going to have any slowdowns. You're going to drop it. We're going to tie it together. It's going to be good.
So we do sometimes perform intermediate checks, probably not on the software side, but quite often on some of the projects. For example, we were dropping a reactor into a building, and what we wanted to make sure is that um, once it's placed and we have our piping ISOs made, that's we're not going to be off, right? So even though we provided detailed drawings for reactor placement, with very very detailed descriptions when it comes to dimensions and the overall details, we still went back and we rescanned, and I mean it was a bit off, so and we adjusted our piping accordingly. Recently, I had a project where we were placing a new tank farm in place with, I think, about a dozen tanks ranging from 10,000 gallons to 50,000 gallons. And one thing we did is um, we laid out anchor bolts for that job. And even though we could use the tank drawings to do our layouts, we didn't. Once the tanks were manufactured, we scanned the tanks and we pretty much extracted the bolt holes diameters and layouts from the scan, and we laid them out based on the data we captured rather than the drawings, which actually helped a lot. There were some tanks where a deviation from bolt circle were inch and a half and above.
Wow.
I want to say, um, pretty often those tanks are actually not that circular, not as circular as you would hope for them to be. So on that job, actually, some of the tank installations went very, very smooth. I think one of the tanks was installed, I think even without any taps. One was installed with just a single tap on one of the anchor bolts.
Wow.
So,
That's pretty good.
yeah, I would say those intermediate steps are quite important. So if we have a timeline to implement something like that in the project, we always try to do that, because the last thing we want is to run into a situation where we put a piece of equipment and something was missed either on design side, which can still potentially happen, or on the installation side, and then we have to do a lot of field modifications, which is always not desirable. So
Yeah.
if we have a timeline, budget, and um, we always try to do that. Yes.
So how much time or budget do you need to kind of get ahead and to do a step like that, to scan a tank ahead of time? So instead of using the drawings that you had, you can place the bolt holes in your own drawing, um, and then overlay that. How when you say you guys need time and budget, how much time and how costly is it to that relative to the end product of shows up and you've got bolts that are inch and a half out of where they're supposed to be because the hole's in the wrong spot.
Time wise, we're always flexible. I think that's one of the things we try to do. I mean, our customer success is our success in the end of the day, and we try to be as flexible as we can be. So there were instances where um, a tank um, would be finished, and then we would scan it the next day. I mean, the same day we would be generating the drawings for the layouts, uploading all of that into the software for the total station. Next day in the morning, we would be laying them out, and I think the same day or the day after they would be drilled. So time, especially when we have capacity to do things like that, um, we can squeeze it in quite fast. Now, this is not a very big scale task, right? But let's say if we would need to uh, scan something more substantial, that might take more time to do the work, process the data, do the design work. So obviously, depending on what we're talking about, it might scale up. But regardless of what we're talking about, we will always try to accommodate for our customers' needs. Budget wise, I mean, in that case, we just needed a couple, half a day of layout work, couple of hours of scanning, and then a couple of hours of drafter work. So it's not that much.
Yeah,
But
not that much, just waiting to drill until after the tank is finished and you get that information over.
mhm,
That's so you said like half a day or something. And that on the field side saves, I mean, those went in about as smooth as they could go, it sounds like.
mhm. I probably should have added some of those videos in this presentation because
That's all right.
I do have a video, but it didn't seem applicable, so I didn't, unfortunately.
That's all right. That's all right. That's still an awesome, that is an awesome use case.
Mhm.
Um, well, Kirill, do you have anything else that you'd like to share? You know, your experience, things that you've learned on you know, reverse engineering with scanning.
Well, in my experience, I mean, scanning simplifies a lot of things quite a bit. I remember at some point I had to model a crankshaft, and back then I didn't even know about scanning. I had to model crankshaft by measuring dimensions, and it took me a lot of time because some of those geometries are not very simple, especially when it comes to curvatures. So I wish I would have known about some of those technologies, but in fact, even if I knew, I didn't have the budget to do anything like that. But perhaps I could reach out to people who knew more than I did or had some of those solutions. So I think um, the fact that we implement some of those solutions is quite amazing because I remember the pains of trying to model while trying to measure it. I spent quite a bit of time in modeling that in SolidWorks, and the worst thing is I didn't really have a way of checking myself. Right, once I'm done, maybe I made a mistake somewhere. How do I verify that I didn't make a mistake? Do I measure everything again? Do I just what do I do? But now, if I have a point cloud or a mesh, simply overlapping my model with a mesh or a point clouds will pretty much take all the questions away, right? It's going to verify that what we did is going to work, and I think that brings a lot of value in itself.
I think that's great. I think that's awesome. I think you guys are doing, you know, your adoption, and as you mentioned, you know, I've seen a lot of your well, not slow, but your, I guess, planned adoption of technology in a way that's been really you adopt it as it adds value, you know, one piece at a time. Obviously, in engineering, mitigating any risk, checking, doing the field side. We talked about that a lot. You know, again, jumping back um, to hand measuring things on site too, but applying the technology in a practical way so that one, you can gain the confidence and trust in the technology as you start to adopt it and learn what the risks are, what the risks are, where it's really valuable, where it's really strong, where its shortcomings are, what you need to do on site to mitigate, any risks so that you can take full confidence in this, but creating a good plan in your adoption of the technology to move from not using it at all to being able to really leverage it to its absolute maximum. And it's not abandoned ship on what people do in the field by any means. It's innovation. It's leveraging the power of these other technologies and these other tools, and not as just an expense, as something like, oh, something extra just to verify and do work. There's, as there is with any new technology, there's that learning curve where you have to take on extra work and effort to learn and implement a new tool and structure in a sense. But by stepping into that, expanding what you're capable of doing, shortening workflows, getting analyses that would otherwise be, I'm sure, really hard for some of these structural elements, now scanning huge facilities and measuring and reverse engineering them where that would have taken huge amounts of time, verifying with hand where it's needed. So really just the really planned and safe approach as you guys have expanded, I think is something that's uh, really valuable, very valuable, and very practical when it comes to implementing and learning these types of tools. The plan of growing your arsenal of tools, is something that requires a little bit of a plan in of itself. I think that's something your team has done very well.
Thank you for saying that, James. Um, I mean, I think it's very easy to look at all the sales pitches and different hardware and software solutions available out there. And it's very easy to convince yourself that, oh, I need this. I will benefit from it greatly. But I like to always step back and see, okay, how can we actually implement it? How disruptive is it going to be to existing processes? Um, can we fully extract value from this hardware or software piece? I think it's quite important. We can try to buy every solution possible, but then what are we going to do with it? If we adopt new technologies, let's try to fully implement it. Let's explore its capabilities. Maybe there are some capabilities that are not even advertised by the manufacturer, and maybe we can implement it in a way that it hasn't been implemented before, which would be great too. But it all requires resources and time and effort. And I think jumping, or I guess not jumping into it, with head first is definitely has been a good approach on our end. We did have our shortcomings. We did purchase a few things, rather cheap things on the mobile scanning platform side, which didn't turn out to be good investments. And we had to learn that post factum. In fact, that platform hasn't been used in about 2 years, and it sits in the closet. I'm not going to say what it is, but it's just a mobile scanning platform, which unfortunately didn't fit our needs. And that's okay. Sometimes that's the way to learn the lesson. I'm just glad it wasn't like a $100,000 scanner, which didn't fit our need. This one was much cheaper.
That's good.
So that's okay.
That's good. Yeah, that's mistakes happen. It's always less fun when they're more costly. That's that's for sure. Awesome. Well, Kirill, thank you for joining us. Thank you everybody for joining us. Like to just give a shout out again, Kirill, for joining, and for everybody here. Kirill's been a pretty active member in some of our committees. In fact, if you haven't participated or haven't been involved in any of the RCN committees, and if you want to collaborate with Kirill or more people like Kirill, we've got a great platform bringing, some of the best minds and users of reality capture technology together to those committees. You can find those just on the Reality Capture website. Great place to virtually collaborate and coordinate. And then for everyone as well, we have our big annual conference coming up to shake hands with Kirill, shake hands with other professionals doing this sort of work in just under a month now. So we are October 7th to the 10th. That's when we have our big annual conference. You'll be able to meet Kirill, you'll be able to meet myself and other professionals, doing this sort of work. So I invite you, come collaborate, learn, from people who are using this technology, implementing it very practical, ways, gaining a lot of value, selling this as a service to owners, to engineers, architects, and learn how people are learning the technical side, learning the business side to help make this really valuable for their businesses. So we invite you there. We look forward to seeing you all there. And again, Kirill, thank you for joining us today. Real honor to have you here with us.
Thank you for having me, James.
Yep. All right. Well, thank you very much, everyone. Hope everyone has a great day.